Wow, I actually did it. I'm in math. This is awesome. It's okay, nothing can hurt me here. Wait a second. Hi everybody, I'm Mr. Wheeler and welcome to another episode of Lost in Math. Today we're continuing our talk on probability and talking about independent and dependent events. Now events can either be independent or dependent. Independent events, the outcome of one does not affect the outcome of another. So one event has no effect on the other event. If they are dependent events, the outcome of one does affect the outcome of the other. So dependent events, one affects the other. So let's look at some examples to get a better idea of what I'm talking about. Example A on your notes. So example A says that you choose a colored game piece from a board game, and then your sister chooses one. And then ask us, are these two events, you choosing a piece and then your sister choosing a piece, are those independent or dependent? They're dependent. If you choose the blue piece, then your sister can't choose the blue piece. She has less options to choose from. So your choice affected her choice. So her choice is dependent on your choice. So this would be an example of dependent events. Example B says that you flip a dime and it lands heads up, and then you flip a nickel and it also lands heads up. So this would be an example of independent events. The outcome of the nickel had no effect on the outcome of the dime. The dime didn't care what the nickel did. It was independent of itself. It just happened to also land heads up. So those would be independent events because one does not affect the other. So suppose an experiment involves flipping two coins, and we want to find the theoretical probability that we get a heads both times. Theoretical probability, we remember, is the number of ways an event can happen over the total number of equally likely outcomes. So if we remember our notes from theoretical probability, card in the top right-hand corner, when we flip two coins, we get four outcomes. I could have got a heads and then a heads, or a heads and then a tails, or a tails and then a heads, or a tails and then a tails. So four outcomes. So how many ways can I get two heads? One, that one. And over the total number of equally likely outcomes, there were four outcomes. So my probability should be 1/4 or 25%. Flipping two coins, those are independent events. What happens to one coin does not affect what happens to the other. So we also have a formula we can use when talking about independent events. The formula states that the probability of A and B is equal to the probability of A times the probability of B. This only works if they're independent events. So let's try it on that problem we did just to make sure it works. So we want to find the probability of getting a heads and another heads. So since they're independent, that should be equal to the probability of getting heads times the probability of getting heads. The probability of getting heads on one coin is 1/2. There's one way to get heads and two total outcomes. So probability of heads is 1/2. Times the probability of heads, which is also 1/2. So the probability of heads and heads equals 1/2 times 1/2, and that's 1/4, which is what we wanted it to be. So the formula works. I wasn't lying. It's true. So on our notes, we have two examples. Why don't you try and see if you could find the probability of both of those independent events. So example A, first it describes what doubles are. Doubles are when you roll a dice and get two of the same thing, so like 2 3s or 2 4s, that's doubles. And it's asked for the probability of rolling doubles 3 times in a row. So probability of doubles 3 times in a row. These are independent events. What happens on one dice roll doesn't affect the next dice roll. So probability of doubles and doubles and doubles should equal the probability of doubles times the probability of doubles times the probability of doubles. So we just need to figure out the probability of getting doubles once and then multiplying it by itself 3 times. When we're rolling 2 dice, each die is its own occurrence. So if I rolled a 1 on my first die and a 6 on my second die, that's different from rolling a 6 on my first die and a 1 on my second die. So if I was looking at the sample space of rolling 2 dice, it would be all of this. 6 ways for your first die to land, 6 ways for your second die to land, so that's 36 total options. So we want to find the probability of rolling doubles. Probability, number of ways something can happen, over total number of equally likely outcomes. So doubles are those guys there. That's 2 1s, 2 2s, 2 3s, 2 4s, 2 5s, and 2 6s. So there's 6 ways for that to happen. Over 36, that's the total number of equally likely outcomes. So chances of rolling doubles, that's 6 over 36. Reduce that fraction, so 1/6. So the probability of doubles is 1 in 6. Rolling doubles are independent events, so the probability of rolling doubles 3 times would be 1/6 times 1/6 times 1/6. So we get our answer of 1 over 216. Example B says that an experiment consists of randomly drawing a marble from a bag, replacing it, and then drawing another marble. It says the bag contains 7 blue marbles and 3 red marbles, and it asks us for the probability of drawing a red marble and then a blue marble. These are independent events because I replaced the marble in the bag. There were 10 marbles in the bag for my first drawing, and then there will still be 10 marbles in the bag for my second drawing, so they're independent. So probability of red and then blue. That should equal the probability of red times the probability of blue. To find the theoretical probability of drawing a red marble, it's number of ways that can occur, so 3 over the total number of equally likely outcomes, 10. There are 10 total marbles in the bag, 7 plus 3, and 3 of them are red, so the probability of red is 3 over 10. Times the probability of blue. There are 7 blue marbles in the bag, so my probability of drawing a blue marble would be 7 over 10. So probability of drawing red and then blue would be 3 over 10 times 7 over 10. So I'd get 21 over 100, or 21%. So I had a 21% chance. What if on example B we didn't replace the marble after the first drawing? That would change this problem from an independent problem to a dependent problem. So the probability would change on this one. So my probability of drawing a red marble the first time would stay the same, 3 out of 10, 3 red marbles, 10 red marbles. But my second probability would change. There's still 7 blue marbles in the bag, but now there's only 9 marbles total, because my first time I took out a red marble and kept it. So there's 1 less marble in the bag. So it would be 3 over 10 times 7 out of 9, which would be 21 over 90, or about 23%. So this brings us to a formula for dependent probability. Probability of A and then B, if A and B are dependent events, it's the probability of A times the probability of B after A. So it's the probability of B happening, but you have to assume that A already happened. So, yeah. So let's try an example. We got another bag of marbles this time. This time there's 6 orange ones and 4 red ones. And I'm going to find the probability of drawing an orange one, a red one, and then another orange one, but all without replacement. So that means after I draw a marble, I don't put it back in the bag. I put it in my pocket or something. So we want the probability of orange, then red, then orange. It's dependent because since I'm keeping the marble, my odds of the next thing are affected by the odds before it. So these are dependent events. So first, probability of getting an orange marble first time around. There's 6 orange marbles in the bag and 10 marbles total in the bag. So the probability of orange is 6 over 10. Now I want to find the probability of red after orange happened. So we'll assume I did my first one perfectly fine and drew out an orange marble. Now we want to find the probability of red. Probability of red, 4 is on top because there's still 4 red marbles in the bag. But my denominator is 9 now because I drew an orange, took it out, and it's not in the bag anymore. So there's only 9 marbles left. Lastly, we want to find the probability of drawing another orange marble, assuming I already drew an orange and a red. So now there's only 5 orange marbles left in my bag. On the first draw, I picked an orange and took it out. So instead of 6, there's only 5. And then in my denominator, there's only 8 marbles left in the bag because I already took out 1 orange on my first pull and 1 red on my second pull. So it's 5 over 8. So the probability of this occurring, orange and then red and then orange without replacement, would be 6 over 10 times 4 over 9 times 5 over 8. So that's 120 over 720. When I reduce that, I get 1/6. So the probability of drawing orange and then red and then orange was 1 in 6, or 16.7%. So that was our video on independent and dependent events. Like the video if you enjoyed it, and as always, I'll see you next time, because I'm stuck here. Bye, guys. The first time. So that would change this problem from dependent to they're stop. When we're rolling 2 dice, each one is its own occurrence. So probability of rolling doubles, there's 30. The probability of drawing a blue and then a pink and then another blue. So that was our video on independent and dependent. So that was our video on independent and dependent probability.